Hi, today we are going to discuss about Parameterizable LMS adaptive filter, and this is my 278 uh, final term project, which has been guided by our professor Dr. Changchu. So, moving towards the introduction of the filter. So, what is an adaptive filter? Normally, an adaptive filter is a system with a linear filter that has a transfer function controlled by variable parameters and a mean to adjust those parameters according to an optimization algorithm. And this adaptive filter is having a very wide use in industry right now, and many FPG applications and DSP applications have been based on adaptive filters. While making an adaptive filter, we'll be using a least mean square algorithm for the design. So, what is exactly the least mean square algorithm? The least mean square algorithms are a class of adaptive filter used to mimic a desired filter by finding the filter coefficient that related to producing the least mean square of the error signal difference between the desired and the actual signal. So normally least mean square will be giving us the difference between the desired output and the actual output, and after the convolution of both the signals we'll get the error signal, and then hence uh, by computing the error signal we'll be getting a proper functionality or a proper function of an adaptive filter. So this is the basic architecture of LMS, where the RAMs are used to store the values of the coefficient. From the RAMs, we'll be taking those values, we'll be calling those values to the LMS algorithm, where it will be computed and the difference will be founded, and then it will be passed to an FIR where the filtration of the signals will take place. So we were provided with an 24 tab 1000 samples MATLAB code through which we generated the coefficients, and by using those coefficients this actual design of the adaptive filter was created. So uh, moving towards the block diagram of the adaptive filter, so here you can see here is the x of n signal coming to the adaptive filter, where the signal is also received, where the filter also receives the signal from algorithm, and the difference between the algorithm and x of n will be getting the y of n, which is not the desired signal but which is the output signal. Once we get the output signal, we'll be checking out with the desired signal. So if the desired signal and the actual signal are same, there won't be any error signal generated. But if there is difference between them, so there will be an error signal generated. And this error signal is generated to the next latency, where the new uh, h of n will be generated, and with the h of n will be getting the uh, will be able to calculate the y of n. So in the block diagram, as you can see, the x and n are input sample which is given to the adaptive filter, and y of n is there generated through it. D of n are the desired output sample given to get convoluted with y of n to get new error signal. After the error signal is generated, it's sent to the algorithm where the signal is compressed so that after a while the output turns out to be 0. This is the actual process of the adaptive filter. Moving towards the algorithm, as you can see, the adaptive algorithm, what we have used. This algorithm was proposed by our professor Dr. Chanchu. So according to this algorithm, so what basically it's happening, there are like MAC which we've been using, where the signals will be getting accumulated, and an LMS logic is also created. As such, LMS engine is created where the entire calculation will be taking place, and you can see there is a controller over there. The controller rule is to control the signals, each and every signal which is coming in the algorithm and which is going out of the algorithm. So the controller controls each and everything in the following uh, design. So now talking about the algorithm, what the algorithm is created, let's talk about it. So initially we'll be having the samples, the input samples which we have calculated through our code, MATLAB code, and then we'll be having the desired signal as well. So initially we'll be taking error signal as 0 and h of n as 0, and we'll be calculating the y of n. So the y of n, for suppose there is a 4 tap filter. So the y of n will be calculated. So there will be a 4 input samples. So it will take for a one y of n to be get calculated. It will take 4 iteration. So that we'll get the value of uh, final y of n, e of n, and new h of n. So the entire process depends upon the number of iteration which will be taking place. It's according to the sample. It's according to the tabs which is required for getting sampled. So initially y of n will be calculated by the formulas y of n plus x of n into h of n, where x of n is the input signal, y of n initially it's 0 and h of n is also initially 0. Then the value of h1 of n is updated at each iteration. Initially, we'll be taking it as 0, but slowly and gradually, once the error signal is generated, it is convoluted with the with the input samples, and the new h of n is generated. As you can see, there is a coefficient, there's a constant mu. Mu is the number of sample used for the computation of the entire signal. At the end of the signal, at the end of the each cycle, we need to update the error signal. For the updation of the error signal, what we'll be doing will be taking the desired output signal and the uh, output which we have received, and then we'll be subtracting both of them, and then we'll be getting the error signal. So the error signal, the last cycle will be the new value of the new cycle, like how the y of as we have considered x of 1. So we'll be after the entire cycle completed, we'll be getting new error signal, and that new error signal will be used for the next cycle, which where x of 2 and x of 1 will be generated and y of 2 will be generated. So this is how the algorithm works. So as the design was formed, it needed to be compiled. So the entire file which we have made, we worked on Altera Quattro tool, where we compiled our design. After the compilation of the design, there was no error, and hence we were, we were given the green signal to go towards the simulation part. So using Model Sim Altera, we simulated the first waveform, where you can see this is the radix form of the signals, where E is generated, where data and reset and start signals are there, and they have been created. So initially you can see there are some values generated over here. So these are like the decimal value, so it's not like it's not like getting convoluted or it's getting zero properly. So for this, what we'll be doing, we'll be giving a right click on any of this signal, and there is an option where the format can be changed into analog automatic. After analog automatic, this is the signal which we have found. So here you can see there is an error signal generated. So initially this error signal are into high impedance. They are going to high and max amplitude, and as the sample number of sample increases, as the number of cycle increases, eventually they get converged and slowly they form into zeros, as you can see. So the complete zero formation is over here. There are little distortion over here as well as little over here. So the reason for the distortion is the noise created in the algorithm. There are few places where the number of samples which we are using will be will be creating some errors or some noise. So after entire zeroing, there will be some distortion, and again there will be entire zeroing. So mainly, you can see that eventually after a certain period of time, this signal is getting converged, and at a particular time over here, it's getting zero, and it turns out to be zero for the entire clock cycle. The next waveform also shows us how the error signal are generated using two types of waveform. The first was the error which is flopped, and this is the error which is we have got. So you can see the normally at a certain period of time, everything is getting converged and it is forming up to zero. So the desired output of this design is when your error signal will be completely getting converged into zero. If it is not getting converged into zero, that means there is some issues with the adaptive filter or with the design. Hence, with my design, with the working of my design currently, eventually after a period of time, it is getting zero. And so we can conclude in the conclusion part that it is completed satisfactory as it has been converged to zero after a certain period of time. And the future of there are a lot of we can modify and we can enhance the performance by pipelining it more, like we can pipeline the filter to the computation speed so that it can be fast, and we can tune LMS effectively with little bit of modification so that it can be working superb, so that and so it can give an correct coefficients and values for the calculation. And if we need to test, we can test the above design by using audio signal and video signal. But for this, we need a DE1 board, and DE1 board or any other FPGA board will work. And we can, with the use of the FPGA board, we can find out the real-time performance of the filter. And if the performance is little less in the actual FPGA board, it can be enhanced and it can be modified with some more of modifications. But yeah, it can be improved in further. It can be tested, and a proper and nicely performing adaptive filter can be formed in future if needed. So concluding with the entire design and with the entire presentation, I want to thank you for the patience, for hearing me out, and for the furthermore information. There is my report attached to it, and you can check it out. Thank you.